That was close. That was a lightning strike. And that would explain why the lack of light. A storm cloud has covered the sun's rays. Right. Sorry, totally distracted. Okay, so yeah, so the denominator could be 0, right? You can't divide by 0. That gives you infinite quantities physics, loads, infinities. So you got a problem. And the solution, in a rather hand-wavy way, given by the authors, was that you can get around this problem by diagonalizing the perturbation matrix in the subset of eigenfunctions where they are degenerate. Now, it wasn't explained clearly, I thought, how that's done. It was just sort of, hand-wavy. So the bit of discussion now, ending this session, is on diagonalization of the matrix a little bit. So hence the plug for the book. So diagonalizing a matrix means, well, without going into the theory of how to do that, in broad terms, it just you're just changing your matrix such that all its elements are 0, except for some along the diagonal. Which diagonal? The northwest, southeast diagonal of the matrix. Those elements become non-zero, or some of them. Okay. Now, the technique how to do that is in this book, for example. Look it up. It's almost at the end of the book. It's back about here somewhere. It's sort of, right? So you need to know a fair dose of linear algebra, and I'll teach a whole undergrad course on it, because linear algebra is really important. It keeps cropping up in all kinds of fields, certainly in quantum mechanics. Okay, so if you have not studied linear algebra before, if you do not know how to diagonalize a matrix, then probably this will seem rather meaningless, incomprehensible. So you'll just have to skip over it, I'm afraid. Okay, so so we getting back to this problem, we need to show the exception that the first order energy shift is not 0 under these circumstances when the momentum is h bar pi over a. So where does that come from? Well, in trying to diagonalize the matrix, the so-called, you need to consider the off diagonal matrix elements. You may ask why. Well, if you don't know how to diagonalize a matrix, don't worry about it. But if you do, you need to do this kind of thing. Now we have two. Now we're talking the matrix whose eigenfunction just wondering how to explain this without giving you the theory, without the whole theory, and the whole theory needs a whole book, right? Because it's at the back of the book. So I'm stuck. If you don't know what it's. I think I'll just throw it at you and jump in. So you need, from the theory of this diagonalizing the matrix, you're dealing with elements that are not along the diagonal, and
a vast virus database has been updated.
Don't ask me why yet. Maybe come back to this after you've done the linear algebra course. Right. So, but we have two eigenfunctions that are degenerate, right? So we can use those two in the here, like this kind of thing. Finding the perturbed energy. Yeah, we can have the bra K and the ket minus K, this kind of thing, for the H bar. Right? Now, if you look at the definition of this term, it's just this. Okay? So what have you done? You just swap these two around. But if you reverse the order of the bra ket, the term in the bra and the term in the ket, if you reverse it, so if you have bra A, ket B, that's the conjugate of bra B, ket A. Did that all way back. Okay, so this is, you know this, right? Now, what is this? Well, here's your V, here's your perturbing term H bar, that's your potential, right? And now, when you put it this way, you end up with it. You end up with this term. They don't cancel. You just get double it. You get a -2. And if you evaluate that integral, it's non-zero in a special case when your k here is plus or minus pi over a. Otherwise, except in that circumstances, it's zero. Otherwise, it's just calculus. Okay, so there's where it comes from. Okay, so if k is this, then you're talking about the momentum, but from the de Broglie formula, the momentum is h bar k. So if you multiply this by h bar, there's the result, right? Plus or minus h bar pi over a. Here it is. So it's zero. Perturbing eigenvalue energy shift is zero, except when the momentum takes this value because of this integral. Now, this sort of part here, you probably could be confused by. Yeah, inevitably. I think you just have to wait until you've done some linear algebra. Now, if you have done linear algebra and you understand linear algebra quite well, then maybe the rather fuzzy explanation of Davies may make some sense to you. So good luck. Alright. Okay, down to this last little bit of this session. Now he's assuming that you do know how to diagonalize a matrix, and it usually involves solving a determinant. A determinant of what? Well, he's not telling you, he's just assuming you know. So diagonalization is accomplished by solving the determinantal equation. So that's also from linear algebra. When you're trying to, if you have an eigen equation, or let's just say an ordinary eigenvalue type equation, so you have the usual form, some operator times a function equals a constant times a function. Now, to solve that, you solve it by using a determinant. So you bring the right hand side over to the left hand side. So then you have operator function minus number, scalar or constant, times the same function equals 0. And that has a solution if the determinant is 0. So then you find the determinant of the left hand side. That's where this kind of thing comes from. So these e's here, they would be your eigenvalues, and so this comes from forming the determinant of that eigenequation. And let's see. So these are zeros, right? We just did that before. So the h, this disappears. So you're just left with this. Similarly with this. Okay. Now, when in the case when you've got k minus k, you've got v over 2, so this becomes just v over 2, right? And that means that E1 is just simply plus or minus v naught over 2. Okay? And hence the absolute shift, one up, one down, because plus or minus v naught over 2. So the difference when you split those two energies is twice v naught over 2, in other words just v naught. I suggest, for those of you who don't know how to diagonalize the matrix, come back to this once you've done this course. When will I be teaching this? I have about a dozen or so undergrad courses that I'll be teaching as preliminary courses to the graduate level stuff. I'm slowly getting an increasing following. I know how many people hit my deGarisMPC website each day because WordPress, they're my more thunder, rain coming, I guess. Is they host my website for free. It's very nice of them, so I'm able to